Okay, so hello everyone. In this video, we will cover MAC protocols, medium or we can say multiple access control protocols. So in this video, we will discuss about MAC protocols and then we will discuss in detail about Aloha, and in Aloha we will discuss pure Aloha and slotted Aloha. So first of all, what are the keywords related to this topic? So first is transmission time. In simple terms, when we are transmitting bits on communication link or channel, that is transmission time. That time is transmission time. Okay, then what is propagation time? Propagation time from sender to receiver. Bits are propagating on the link or channel. This is propagation time. Okay, and then the last keyword, vulnerable time. What is vulnerable time? The length of time in which there is a possibility of collision. That is vulnerable time. Now, first of all these protocols basically come under the data link layer. In the data link layer, we have two sub layers. One is LLC, that is logical link control, and then other one is MAC, that is medium access control. Okay, the LLC here is used to control the link. Okay, this means if I have to send data from sender to receiver, we need to understand how we synchronize frames, how we detect errors, try to correct errors, and how do we control the flow of data transmission. Okay, we discuss all that in LLC. I want to tell you that I have already made videos on these topics. What are the responsibility of data link layer, how do we do error control, but in this video we are talking about medium access control protocols. Okay, which comes under MAC. You can call it medium access or multiple access control protocols. Okay, what is the fundamental concept here? Basically, when we talk about links and different stations, let's consider a LAN scenario. Okay, if there is a LAN and different stations are connected to each other in that lane, how can they be connected? Okay, the link that connects them is basically of two types, either point to point, like in mesh topology. For example, if there are four stations, all these stations will be connected to each other point to point, meaning each station will be connected with every other station through a different dedicated link. Okay, in this case, the concept of medium access control protocol or multiple access control doesn't apply. Okay, why? Because the fundamental principle applies only where people are sharing resources. The concept becomes important when there is a one shared link, like in bus topology there was a one link. So here we need control mechanism. If multiple stations are transmitting data at the same time on a shareable link, and if they do it simultaneously, then there are high chances of collision. Okay, if collision happens, then all your data will be wasted. So what do we actually have to control? We have to control collisions. Now we have three main categories in which we divided these protocols. First category is random access protocols. Random access protocols means in which there is no priority system. If we talk about a scenario where there are different stations A, B, C, D, the priority of all four stations is exactly the same. Second characteristic is that these four stations can send data at any time. Okay, there is no scheduled turn system, like now it's A's turn, now it's B's turn, like nothing like that. Okay, in the random access category, we generally have Aloha, CSMA, CSMA CD, and CSMA CA. If we talk about medium access protocol, the most important topics among them are CSMA and CSMA CD. Okay, in numerical problems, if we consider Aloha, there are two categories, pure Aloha and slotted Aloha. In these, we generally discuss vulnerable time. We also discuss throughput and efficiency. Similarly, if we consider CSMA and CSMA CD, here we have collision detection and collision avoidance respectively. Okay, CD means collision detection and CA means collision avoidance. Then we come to controlled access protocols, which include polling and token passing control. Control means someone is controlling the access here. Okay, polling is like conducting a poll. If there are four stations and all four want to transmit data, then we will take a poll before transmission. Okay, polling means we decide whether A will transmit first or B will transmit first or C will transmit first or D will transmit first. Okay, the station that wins that polling process will transmit the data. Okay, while others will not transmit the data at that time. Okay, talking about token passing, what do we have in token passing? We have token ring topology. I have discussed it in previous videos. Okay, question can come on throughput and efficiency calculation here as well. Okay, now after controlled access, we discuss channelization protocol. In channelization, we use proper dedicated channels like FDMA, frequency division multiple access, and TDMA, time division multiple access. We use the concept of multiplexing here, in which we divide frequency band into fixed channels and assign them one by one to different stations, so that each station can use that specific frequency to transmit data. Now we are going to discuss pure Aloha in detail now. Okay, the first important point is the pure Aloha is a random access protocol. Random access protocol means that we have not given any schedule time to any station. Okay, there is no rule. This means any station can transmit at any time. Okay, So the question naturally arises here, is collision possible in this scenario? Let's say we have this shared media. Okay, this media is shared by these four nodes A, B, C, D. Okay, in this setup, nodes A, B, C, D can start transmission at any time they want. Okay, when they get data to transmit, they will immediately start transmission. Okay, we will not sense the carrier first, meaning we won't check whether data is already traveling on the medium or not. Okay, as soon as we get the data, we will immediately transmit it on the shared medium. Okay, so obviously collision is not just possible but highly probable here, because at the same time it is very likely that some other station is also doing transmission. Is there an acknowledgement mechanism in pure Aloha? Yes, acknowledgement is definitely present in the system. Let's say if station A sends data to station C, as soon as station C receive the data successfully, meaning if collision does not occur during the transmission, then station C will send an acknowledgement back to the station A confirming that yes, I have received your data. This acknowledgement system was implemented in pure Aloha. Okay, but what if acknowledgement doesn't come back to the sender? If acknowledgement doesn't arrive, what does that mean? It means collision has occurred during the transmission. We can use the backoff method here specifically for retransmission methods. Pure Aloha is a LAN based protocol, so we are talking about relatively short distances because this is a LAN based protocol. We consider only retransmission time in calculations. Okay, we don't consider propagation time. Why? Because in LAN environment the distances are so small that propagation time becomes negligible compared to transmission time. When we talk about transmission time, to understand this entire algorithm and protocol properly, we assume fixed time slots. This means the transmission time is fixed for all station and all messages. Now let's talk about vulnerable time. What is the fundamental concept of vulnerable time? Let's say this is my timeline, and on this timeline I am at the point T. I start my transmission at point T. As soon as I start transmission, my bits start traveling one by one on the shared medium. Okay, what does transmission mean? Transmission mean I calculated as message size divided by bandwidth. Okay, let's take a practical example. Let's say my message is 1000 bits in size. My message is 1000 bits and channel bandwidth is, let's say, 100 kilobytes per second. Okay, so what is the total transmission time? This becomes 10 milliseconds. This means for 10 milliseconds I will keep transmitting bits continuously on shared media. Let's say this 10 millisecond duration represent my transmission time. Okay, now during these 10 milliseconds, if any other station start transmitting, what will happen? Collision will definitely occur. Okay, let's say someone start transmission here, collision occur. Someone start here, collision occurs. Even if it's very last moment, if my last bit is traveling to the channel and at the exact same time someone else start their first bit, then my last bit and their first bit will collide. Even one bit collides, then the entire message gets corrupted. Okay, so during this entire time period, during these entire 10 millisecond, or you can say during this entire transmission time, no other station should transmit. This is the one part of vulnerable time. But there is another aspect to consider. I started transmission from time T, and this time T can be anything, 11 am, 12 pm, 1 pm, anytime. Okay, but it is also possible that before my transmission time someone else has already started their transmission, and if their transmission also takes 10 milliseconds, then ideally their message should finish completely before I start. Okay, but in the worst case scenario, it is also possible that their last bit is being transmitted and the exact same time when I start transmitting, my first bit will collide. Okay, in that case my message and their message will be definitely collide. Okay, so what is the vulnerable time? It includes the transmission time during which I am transmitting, during which no one else should transmit, plus the transmission time before I start, during which no one should have started transmitting either. Okay, otherwise their transmission might overlap with mine. Okay, this is how we calculate vulnerable time of pure Aloha. After I start my transmission, for the duration that I am transmitting, no one else should transmit. Okay, and for the same duration before I start, no one should have started transmitting either, because if they did, collision will occur. That means for a total duration of 2 into transmission time, if anyone else transmits, then collision will occur. But if the gap between transmission is more than 2 into transmission time, then there is no problem. Okay, no collision will occur. So here we have our first formula. Vulnerable time equal to 2 into transmission time. You can say vulnerable time is 2 into 10, 20 millisecond according to this example. Okay, next we have efficiency calculation. Efficiency we denote by eta, and the formula of efficiency is eta equal to g into e to the power minus 2g. Where does this 2 come from? This minus 2 comes directly from the vulnerable time calculation. What is this g? G represents the number of stations that wants to transmit data during a particular transmission time period. G is the the number of station that want to transmit data at a particular time slot. Okay, many time in exam you have asked like what is the maximum efficiency of pure Aloha. After derivation of efficiency formula, we got G equal to 1 by 2, or we can say 0.5, and e's value is fixed 2.71828. Okay, after calculating these, we got maximum efficiency of pure Aloha is 18.4%, which is quite low compared to modern network standards. Okay, what does this mean in practical terms? If your bandwidth is 100 kbps, then out of 100 kbps you can only utilize 18.4 kbps effectively. Okay, all the remaining bandwidth gets wasted due to the collisions. Okay, now we are going to discuss slotted Aloha. The first major difference between slotted Aloha and pure Aloha is the timing mechanism. In pure Aloha, transmission can be started at any time, meaning any station at any time can start transmission without any restriction. Let's say this is my timeline and this is progressing in the direction. Okay, in pure Aloha, anyone could start transmitted at any point on this timeline, but in slotted Aloha, we divided this continuous timeline into discrete time slots. What is the duration of each slot? We made this duration exactly equal to the transmission time. This means the time taken by one station to transmit its complete message, that duration became equal to one time slot. I have already assumed transmission time to be fixed for all station. Okay, what is the transmission time? It's message size divided by bandwidth. We always assume that the transmission time is fixed. Every message takes exactly the same fixed time to transmit. Okay, but simply dividing time into slots is not enough. But we introduce a second important condition in slotted Aloha. Any station will start its transmission only at the beginning of time slot. When a new slot begin, only at that precise moment can transmit start. Okay, transmission cannot be started in the middle of the slot, at the end of the slot, or any of random time. Okay, this condition is strictly enforced in slotted Aloha. What is the fundamental concept of vulnerable time? Let's say this represents one time slot. Now, if station start transmission in this slot, where will it start? It will start right at the beginning of the slot as per our rule. Okay, A start transmitting from the beginning of the slot and continues putting its bit one by one shared medium throughout this slot duration. Okay, now if another station want to transmit during this slot, they cannot start anywhere. Okay, in the middle of this slot. Why? Because of the condition we established. Transmission can only start at the beginning of the slot. But it is still possible that 2 or 3 multiple station might try to start transmitting at the exact same time. Okay, right at the beginning of this time slot. In that case, collision is still possible. Okay, when is collision possible in slotted Aloha? When 2 or more stations start transmission simultaneously at beginning of a same time slot. Okay, so in slotted Aloha, vulnerable time equals what? It equals exactly one transmission time, because the duration of each slot is equal to transmission time. So vulnerable time in slotted Aloha is equal to transmission time. Because of this reduced vulnerable time, the efficiency formula also changes. If we calculate the efficiency of slotted Aloha, the formula becomes eta equal to G into e to the power minus G. Okay, after derivation of efficiency formula, we got G equal to 1. This means on an average, if exactly one station transmit per slot, you will get maximum efficiency. If only one station transmit in one slot, it will be completely collision free. After calculating max efficiency of slotted Aloha, then max efficiency of slotted Aloha is 36.8%. Compare this with pure Aloha's maximum efficiency. That was 18.4%. Slotted Aloha achieves exactly double of the efficiency of pure Aloha. Okay, that was the difference between pure Aloha and slotted Aloha. So that's it for this video. We will meet in next video. Until then, bye bye.